In this video, we'll be looking at the resolution of vectors, where we are going to consider the magnitude to bearing form of vectors. And if you have not subscribed to this channel, kindly subscribe and hit on the notification bell so that when a new video is being published, you are going to be the very first person to be notified. Remember that this is BakoMaths and we are thinking beyond infinity. Now let's get started. In the representation of vectors, vectors are represented in 4 ways, and these are: 1, you have the diagram or graphical form; 2, you have the component form; 3, you have the Cartesian form; and 4, you have the magnitude bearing form. So the graphical form, we are saying that you have the vector OA. Then to represent this vector OA in diagram form, then we are going to consider the x component of the Cartesian plane and the y component of it. Now, in this Cartesian plane, its origin is O, and there is a vector A here. So this is how we can represent the vector OA in graphical or diagram form. Now, the same vector OA, we want to write it in component form. So with component form, then we are saying that we can write it as the x coordinates of the vector and then the y coordinate of it. That's the component form. Now, in terms of a Cartesian form, then we are considering the same vector OA, but in this case, we are looking at the ith component of the vector, that is xi, and then the jth component of the vector yj, and this becomes the Cartesian form of the vector OA. The next one here is the magnitude to bearing form, and the magnitude to bearing form of the vector OA simply means that we are going to take into consideration the length or the modulus of the vector OA. That becomes the length of the vector OA, comma, the bearing. So the bearing basically talks about the direction of the vector OA. So to find the direction of the vector, then you have to consider it from the positive y-axis to the clockwise direction to where the vector is. That is the positive y-axis to where the vector is. Now it becomes the direction of the vector. So it means that with this vector, its direction is given out here. You have here as alpha. So this becomes the magnitude bearing form of the vector OA. But in this video, we are going to look at how we can change a vector in the Cartesian form to the bearing or to the magnitude to bearing form. A vector in the Cartesian form to magnitude to bearing form. So this is what this video is about. Now let's take practical examples on how to change the vector from Cartesian form to magnitude to bearing form. We have here as example 1, and it says that write the following vectors in magnitude to bearing form. And there are quite a number of examples, and this is the first one. It says that the vector A, that's the position vector A, is equal to 4i plus 3j. So we want to find solution to this by changing it to magnitude to bearing form. Now the question says that the vector A, which is equal to 4i plus 3j. From the question, it's saying that we should find the magnitude to bearing. So we should find the magnitude first. So it means that the magnitude of this vector is basically about the length or modulus. So that's the length of the vector A, which is equal to the formula, that's the square root of x squared plus y squared. So the magnitude of A is equal to square root of, now x here is 4, so we take it squared, and then y squared, that is the 3 squared here. So to continue, then we can see that the magnitude of A is now equal to square root of 25. And square root of 25 here is the same thing as 5. So the magnitude here is measured in units. So we have 5 units. So we have been able to find the magnitude now. Now the next step is for us to find the bearing. So we have to divide our board here so that we can focus on the bearing. So you find the bearing, then we have to graph this vector given to us, and with that we can easily find the bearing of this vector. So beautifully we can write here as the bearing form. So we are now looking at the bearing form of the vector, and we are seeing that you should graph this. So by taking into consideration the Cartesian plane. Now with this vector is made up of the j and then I component. So the I component has the x-axis we know to be 4. So write the 4 here. And then the y-axis we know to be 3. So write the 3 here. So it means that this vector can be found in the first quadrant. So that is, we draw our vector this way, labeling it here as the vector E. So once we have this, we could see that we've been able to graph this vector. Now to find the bearing, then the bearing is measured in the geographical north or positive y-axis in the clockwise direction to meet where the vector is. That is, we're saying that to get a bearing of the vector, we have to move from the positive y-axis to where the vector is, and that becomes the bearing. So since we don't know that angle, then let's represent it by alpha. So right here by alpha. Now with this, we cannot directly find alpha, which means that we have to take into consideration the angle the vector makes with the x-axis. And with that, we are going to apply trig ratio to get that angle. And then we consider the quadrant in which this alpha lies and the angle it makes the x-axis, and we can easily get the value of alpha. So we are adopting that strategy because we cannot directly find alpha here. So we have to consider the angle this vector E mixed with the x-axis, and that angle is what we can see here as theta. So represent theta where the angle mixed with the x-axis, and alpha, that is the direction or the bearing of the vector. So it means that once we have this done, then we can close this side of the vector and we can see that it becomes a right angle triangle, knowing what that this place is the 90 degrees angle. So the best trig ratio we can use in considering this right angle triangle here is tan theta. So which means our tan theta now is equal to the opposite side here we know to be y, and then the adjacent side we know to be x. Now here we can see that this is the x-axis and it's 4, and this side is the y-axis and it's 3. So write that one here. So basically we can see that tan theta now, our tan theta now is equal to our y value here we know to be 3, and then our x value we know to be 4, which implies that theta is equal to the tan inverse of 3 on 4. And that is basically the same thing as theta, being equal to, so you know the tan inverse of 3 on 4 is giving us to 4 decimal places, that is 36.8699 degrees. So you have the theta now, but theta is not the bearing or the direction of the vector, but the direction of the bearing of the vector is giving us alpha. So it means that to find alpha, then we can see that this vector happens to fall in the first quadrant, this Cartesian plane. So now let's analyze something here. If we are saying that this side of the vector is the bearing, that is alpha, and this side is theta, then we know that when we consider this side of the Cartesian plane, total or the sum of angles here is 90. So the sum of angles in the first quadrant of this Cartesian plane is 90. And we are saying that we know the whole of this side to be 36.899 degrees. And we know the sum of the angles here to be 90. Then to find alpha is basically going to be 90 minus theta. So that is what we are trying to see. So it means that the bearing now, that is alpha now, is equal to 90 degrees minus our theta here. But we know theta to be the same thing as 36.8699 degrees. So basically our alpha now is equal to 53.1301 degrees. So this becomes the bearing of the vector. So now the question said we should write the following vectors in magnitude bearing form. So we know the magnitude to be 5 units, and now we know the bearing to be 53.1301 degrees. So now let's write therefore. So we write here as therefore we can see that in magnitude to bearing form, we can see that the vector E is equal to, that is the units, 5 units, and the vector, and the direction and the bearing. Good. But we know that bearings are written in 3-digit angles. So this side we can see that it is only 2-digit here. So it means that we have to write 0 here. We have to write the next one as 53. Now we have the 3-digit angles before the decimal. So we write the 1301 degrees beautifully as that. So this is how we can write the vector A equals 4i plus 3j in magnitude to bearing form. I believe this is clear now. Now let's move to the next examples for more understanding and clarification. The next example here, that example 2, it says that we should write the following vectors in magnitude bearing form. That we have the given vector here. So we continue with our solution. And the given vector here is, that's the position vector, 5i minus 4j. So first, since the question is saying magnitude bearing, then we have to find the magnitude. So the magnitude of A here is basically about x squared plus y squared. So A magnitude now is equal to the square root of, that is 5 squared plus, now we know our y to be minus 4. So put it in brackets, squared. So this becomes A magnitude, which is equal to, so when we sum this, then we are going to have 41. And 41 in decimal, we know everything to be 6.4031 units. I mostly leave my decimals to 4 decimal places because that's the standard one. So we have this. Now the next one is for us to find the bearing. So once you have the magnitude, then we find the bearing. So in getting the bearing, it becomes so easier if we can easily represent it in diagram form. So we have the bearing form. So first, if you are dealing with the bearing form, then we should have a Cartesian plane here. Now the vector has the parts, that is the x here, we know the x to be 5. And then we know the y to be -4, which means we locate that one down here. So it means that the vector happens to fall in this quadrant. So we draw our vector this way. Now we label it as such. So here we can see that we want to find the bearing. Now the bearing, like we said, is measured from the positive y-axis or the north part of the Cartesian plane. So if you stick to the positive y-axis, clockwise movement to where the vector is, then we are talking about from this positive y-axis to where this vector is. Now I think I have to use blue so that we get it. So that is from the positive y-axis to where the vector is, gives us the direction of bearing. So we represent that one by alpha. Now if that is represented by alpha, then so we represent that one by alpha. Good. The next one here is that since we cannot directly find the bearing using the alpha angle, then we have to consider the angle this vector makes with the x-axis. The angle this vector makes with the x-axis. So we represent that angle by theta. So if that's the case, then let's represent that angle here by theta. So here, if that's the case, then we can join this part of the vector to form a right-angled triangle. So if that happens, then we can see that there is a 90 degrees angle formed here. So we are going to use the trig ratio tan to get the value of theta here. So when we get it, then that will help us to get the value of the bearing alpha. This means that our tan theta is equal to y on x, which means that tan theta is equal to, our y here is -4. But remember, when finding the angle, we don't include the negative because the negative here is letting us find where we can locate the vector in the Cartesian plane, but not necessarily use in the calculation of the angle. So we ignore the negative here and we write our 4 on, we know the x here to be 5. So simply, it means that our tan theta here, that's we finding theta, means theta is equal to tan inverse of 4 on 5. 4 on 5. I think we have to erase it and write it properly. So tan inverse of 4 on 5 here. And theta now is equal to, so the tan inverse of 4 on 5 is given as 38.6598 degrees. 6598 degrees. So we have our theta here to be this. Now, theta is not the bearing of the vector, but the bearing of the vector we know to be alpha. So in finding alpha, then we are saying that the bearing of the vector, that is alpha, start from the positive y-axis to where the vector is. So which implies that from the positive y-axis to this point of it is 90 degrees. And when it continues, that means that we are adding the 90 degrees to the vector, to the angle theta. So it means that the angle theta plus this side of it, that's the alpha, forms the direction or the bearing of the vector. So it means the whole of this side is the bearing of the vector. That is, the summation of alpha and theta gives us the bearing or the direction of the vector. So it implies that to find alpha, that's the bearing of the vector, is equal to 90 plus theta. So it means that alpha now is equal to 90 plus, now we know theta to be 38.6598 degrees. So it means that alpha now is equal to, when you sum everything, you have 128.6598 degrees. So you have it as that. So you have the bearing now to be 128, that is 128.6598 degrees. Now we have to conclude by saying that therefore, in bearing magnitude form, I mostly say bearing magnitude, that should be magnitude bearing form, then we are saying that A is now equal to, the magnitude we saw to be 6.4031 units. And this side, we can see that the bearing here is already in 3 degrees angle. So we leave it like that and write the same thing here. 128.6598 degrees. And this becomes the bearing magnitude form of this vector. Now let's move to the third example. Now these examples are helping us to easily focus on the bearing, how to calculate the bearing of each of the set of problems given. So stay tuned as we move along to the next example. So you have example 3. This is the last part 1. And if you really understand what we are doing here, you can pause the video and try your hands on this question. And later, you can unpause it and watch the solution as well. Now we continue with our solution here. Now, just like we are doing, we want to find the magnitude to bearing form of the vector A, which is equal to minus 6i minus 4g. Now we have this, so first you have to find the magnitude, and that is basically equal to the square root of x squared plus the square root of y squared. So here we know the magnitude of x squared here is minus 6 squared plus minus 4 squared. So here we can see that the magnitude of A now is giving us, so that is the square root of 52. And we know that the square root of 52 here is equal to, that is 7.2111 units. So we have the magnitude of the vector as this. Now the next step here is for us to find the bearing. We are going to look at the bearing. So the bearing form of this, like we usually say, we first have to graph this, and that will be the very easiest way in getting the bearing of the vector. So we graph it, a Cartesian plane. So here, remember that the x part of this vector is negative 6. So we locate our negative 6 here, and then the y part here is negative 4. So negative 4 here. So you can see that this vector will lie in this quadrant. That is the first, second, third, fourth. That is when we are talking about the bearing quadrant. Okay, talking about the bearing quadrant, then it starts from this way: 1, 2, 3, 4. But if we are talking about the trigonometric quadrant, then it goes this way. You have our 1 here, 2, you have our 3, and 4. This is the circled one, is when we are talking about the trigonometric quadrant. But if you are not talking about the trigonometric quadrant, talking about the bearing quadrant, then it starts this way: 1, 2, 3, 4. So if this is clear, then we follow by using the bearing quadrant when we are dealing with questions that involves bearing. So that is great. So it means that this vector would fall in this quadrant. That happens to be the third quadrant when we are dealing with bearing. So you have this here. So this is our vector E. Now we can also close it to have our right angle triangle here. And when we talk about the bearing, then we are considering the direction from the north pole or the positive y-axis to where the vector is in the clockwise movement. So here becomes alpha. That is the bearing of it. But we cannot find alpha here unless we represent the angle it makes, the vector makes with the x-axis by theta. So it means that we can represent the whole of this side here. I think I can use black as well. So the whole of this side by theta. And that will help us to get theta. And doing so, we can easily get alpha as well. So in finding theta, then we can consider the trig ratio tan theta, which is equal to y on x. So just like we explained, we are going to ignore the negative parts of y and x, which means that our theta is equal to the tan inverse of y is becomes 4 now, and then our x is 6, which means that our tan theta here, our theta here is equal to, so the tan inverse of 4 and 6 is giving us 56.3099 degrees. So we have it as that. So it becomes the value of theta. But like we said, theta is not the angle. Oh, sorry, theta is not the bearing. The bearing here is alpha. So here we can analyze it this way. If from this side up to that side gives us alpha, Then to find theta, we cannot add theta to alpha, because from here, this side is 90, from here to here is 90, and then from here to here is another 90, which means you have 180 here. But if theta happened to be at this side, then we could easily add 180, that is 90 plus theta. That gives us 180 plus theta, and easily we can find alpha. But in this case, theta is inside the right angle triangle here, which means you have to consider the quadrant in which theta finds itself, and it's in the third quadrant of an angle of 270. So it means that to get alpha, then basically going to be alpha, which is equal to 270 degrees minus theta. So here we can see that alpha is equal to 270 minus 56.3. So I think you have to write 56.30. Okay, let's erase and write it all. So we have 56.3099 degrees. So you can see that our alpha now is equal to 236.3099 degrees. So we have our alpha here. Now we have to conclude by saying that therefore in magnitude bearing form, we can say that A, that's the vector, has 7.2111 units with the angle 236.3099 degrees. And this becomes the magnitude bearing form of the vector is equal to -I, -4G. Now we move to the last set of questions for today's video. Stay tuned as we walk through together. So that is example 4. And example 4 also talking about we finding the magnitude bearing form of the vector A, that is equal to -2I plus 3G. You can also pause the video and try your hand on this video, on this question specifically. So here we have our solution. We have A, which is equal to -2I plus 3G. And we are saying that the magnitude of A is now equal to the square root of x squared plus y squared. So our magnitude of A is now equal to the square root of -2 all squared plus 3 all squared. So here we can see that when we simplify everything, our solution becomes square root of 13 here, and which becomes a magnitude of 3.6056 units. So this becomes the magnitude of the vector. Now the next one is for us to find the bearing. So in finding the bearing, so let's write a bearing so that we get it easily to the bearing form. Then we are seeing that we have to graph it. So we graph it by drawing the Cartesian plane. So here we can see that our x here is minus, so that is -2. And then we also know that our y here is positive, so we have our +3 here, which means that the vector lies in this quadrant, that is the fourth quadrant here. So we can close this side of it, and you can see there's 90 degrees angle from here. So the bearing of this vector starts from the positive y-axis to where the vector is, and this becomes the bearing of it. So let's represent that one by alpha, but we cannot find alpha directly unless we represent the angle the vector makes with the x-axis by theta. So here, you can say that let's represent this side, this portion of it by theta. So I think we can represent this portion of it by theta. Good. So if that's the case, then we can apply our trig ratio. That is the tan theta, which is equal to y on x, which basically means that theta is equal to tan inverse of, our y here is 3 on 2. So we have that. So we ask ourselves, what is that? Is theta now is equal to 56.3099 degrees. So once we have this, so now we have our theta here, and the next step is for us to find alpha. So that is the bearing itself. Good. I'm having a problem with this pen. Good. So once we have this, then we can equally divide this line. So to find alpha, then it means that from in the first quadrant we have 90, and you continue to the next quadrant we also have 90, and to the next quadrant we have 180, but it continues to where the vector is. So that is 180 plus theta gives us alpha. So it means from the north pole, the positive x-axis, to where the vector is, takes into consideration theta itself. So that becomes alpha now, which is equal to, so that is 90, 180, 270 theta. So 270 plus theta, that is alpha 270 plus, now our theta here is 56.3099 degrees, which means that alpha now is equal to 326.3099 degrees. So once we have this, then we can finally conclude by saying that therefore in magnitude bearing form, in magnitude bearing form, you can say that A is equal to, now the magnitude here is 3.6056 units, comma, the direction here is 326.3099 degrees. So we have it as that. So basically this ends to this video, and we end everything here. So thanks for watching. Kindly like, comment, subscribe, and share. Remember that this is BakoMaths, thinking beyond infinity.